大家好，我是国立清华大学电机系黄眼介。Today we're going to talk about electromagnetic wave in materials. Previously, we always focus on the discussion for a wave propagating in vacuum. Now, when we propagate a wave into a material, then we have to consider how the wave will interact with material. And we have to categorize different materials. The first material we're going to talk about is going to be a conducting material. Then we're going to define surface impedance because the impedance tells you how the wave will propagate into some conducting material. And then we're going to introduce you prisma and then try to understand how a wave will propagate inside a prisma. And when we propagate a wave into a dielectric material, we have to deal with the electric field interacting with the molecules inside the material. And so we'll be talking about how a wave could be absorbed inside a dielectric material. And as usual, we're going to talk about some conclusions before we close this session. So the first session of my lecture today is going to be propagating a wave into a piezo conductor. And I just told you that now we have to understand how a wave will interact with materials. And we know that there's an electric field and magnetic field inside a wave. Therefore, the field will pull the charges inside a material. In particular, the electric field is going to pull electrons, ion, inside the material. So this electric field is particularly important when we discuss a wave propagating inside a material. And previously, we have a solution of the wave propagating along z direction, polarized along x direction. And the propagation is manifested by this k propagation constant, which is equal to the angular frequency multiplying with the square root of mu epsilon. And you can see that in this propagation term, mu epsilon are related to materials. So the material property, in fact, is buried inside this mu epsilon. And when the wave propagating into a material, the electric field can interact with charges directly because you just pull and push the charges. But the magnetic field cannot interact with the stationary charge because the Lorentz force equation tells you that the magnetic field only exists if you have moving charge. So quite often that we just drop this mu in our discussion. So in this lecture, we'll be trying to find out epsilon, which is the permittivity of the material. And then we put into this solution and find out how a wave could propagate inside a material. So specifically, we is going to redefine this epsilon. And inside the material, this epsilon is usually a complex number. And once the epsilon becomes a complex number, then the propagation will be a complex number as well. So we rewrite this k, jk, into gamma, just like the way we define in a transmission line. And then we put this complex permittivity into this expression. And then try to solve the gamma with the real part and also imaginary part. And put this solution back to the Helmholtz equation. And then you will end up having this kind of expression. And this means that the new expression will consist of this exponential minus alpha z and also the propagation term with a propagation constant beta. And the first term is going to tell you how the wave will be attenuating inside a material. And the second term still is the propagation term of the wave. So this is the theme of this lecture. We'll be looking into epsilon for different materials, including conductor, plasma and also dielectric. So now let's start the lecture with the piezo conductor. And for different materials, you need to identify the major difference in the material property. For example, a conductor is neutral, but this material has a lot of free moving electrons. And I took these 3 photos, and in fact, I show you these 3 photos before in the lecture 6.1 and also 11.3 in the electromagnetic 1. And this is a piece of big inductor. I took it from a high voltage modulator in my lab. And this is a copper wave guide, and this is the piece of microwave electron gun designed by the Taiwan synchrotron facility. And all those materials are made of good conductor with a lot of electrons inside. And if you send the electromagnetic wave into such a material, the electric field is going to pull electrons and generate current. And those copper materials, copper devices, are ohmic materials. It means that when you send a current inside this material, the electron is going to collide with the matrix of the material and generate some heat. And during this colliding process, the current is going to be proportional to the electric field, and the proportional factor is called conductivity. And if you flip the conductivity, then 1 over sigma is called resistivity. So we have to put this into the Maxwell equations and then try to understand how a wave could propagate or attenuate in such a material. So let's pull out the Ampere's law, which is curl of E equal to the time derivative of the electric flux density plus the current. So we identify that there's a current term in this expression. So let's put in the current from the last page for ohmic material and just put it into this location and write it like this. So this expression now relates the magnetic field and also the electric field, because this D is also proportional to the electric field. And we only deal with harmonic field. So let's adopt the phasor notation. So we change this equation to this one by adopting the phasor notation. And then you combine these 2 terms and write D equal to epsilon E. So you combine these 2 terms and end up having this expression. So on the left-hand side, you still have curl of H. And on the right-hand side, you have some parameters multiplying with the electric field. And if you compare this expression with the previous one, then you're going to see that this parameter is going to play some role in the propagation of the propagation of the wave inside the material. But 1 plus sigma over J omega epsilon appears to be complicated. So assume that we have a good conductor with a high conductivity, and also set some frequency that is often in our application. For example, if we set this frequency to be about megahertz in the microwave range, then we end up having this term much larger than 1. So this means that we could simplify the expression by removing this 1. So for a good conductor, the magnetic field and electric field are going to be connected through this expression, and you don't have this 1 in this expression. So this is the ideal situation where you have high conductivity. And for example, this value comes from copper. And also we set the frequency up to this value. But of course, if you continue to increase this frequency, the approximation might not be valid, because the 1 over omega is going to become smaller. So let's first just use this approximation and continue our calculation. So if you compare the Ampere's law with the law in vacuum, this is going to be epsilon 0. And then now we have this G omega sigma over G omega. And so with this approximation, we can just take out this 1, and then we can get relative permittivity multiplying with the vacuum permittivity to be equal to this value if you compare this term with this epsilon. So now in a piece of conductor, you can redefine the permittivity through these two expressions. Just make a comparison of them, and then you come up with this conclusion. With this redefined permittivity in a piece of conductor, then you can start to calculate the propagation constant and also the attenuation coefficient inside this material. But before we do that, I want to remind you that in general, the effective permittivity is going to be a complex number if there's attenuation inside. And we have introduced this concept before when we talk about transmission line. So now let's use this permittivity for the conductor and continue our calculation. And remember that in our previous plane wave calculation, we have this jk equal to j omega multiplying with the square root of mu epsilon. Now let's replace this epsilon with this effective permittivity derived for a good conductor. So just put this into this epsilon and do the calculation, and then you will come up with real part and imaginary part in this calculation. And specifically, you end up having the term that is the 1 plus Ga multiplying with this term. And this 1 plus Ga comes from the square root of Ga inside this this part of the calculation. Because when you put this into this calculation, this 1 over Ga gives you minus Ga inside this square root. And square root of Ga gives you exponential Ga 45 degrees. So that's why that you have 1 plus Ga in this expression. But one thing you need to be careful that now for alpha and beta, they are related to the frequency of the wave and also the conductivity of the wave. So if you put this into the solution, then the electric field phasor is going to have this form. You have some amplitude in front of it, and then you have a propagation term that is exponential minus j beta z, and then you have exponential minus alpha z that give you attenuation over distance. And for this particular case, because of this 1 plus j, your alpha beta are the same as a function of the frequency and also conductivity. So this means that the frequency matters, and also the conductivity of the material also matters for the propagation of this wave inside a piece of good conductor. So let's just try to plot this signal. When we plot the signal, we prefer to transform this to the real signal. So you transform a phasor into a real signal by multiplying the phasor with exponential j omega t and take real part of it. So you end up having this expression, and this cosine term gives you the oscillation of this curve in this plot. So imagine that the conductor boundary is right here, and then the wave propagating into the conductor over distance z, and the oscillation is manifested by this oscillating curve on this plot. But at the same time, you have a term that is exponential minus alpha z that gives you attenuation of this wave inside the material. So that there's exponential decay of the wave inside the conductor if you try to send an electromagnetic wave into the conductor. And how long you can propagate the wave inside the conductor is defined by a term called skin depth. So think about that you send a wave into a piece of conductor and the wave attenuates to about 37% of the maximum value of the electric field on the surface. And this distance is called the skin depth in this process. So apparently when this field dropped to 1 over E point, which is the 37% of the maximum field, you set this Z equal to 1 over alpha. So the skin depth is equal to 1 over alpha, where alpha is the attenuation coefficient of this wave expression. So a skin depth is going to tell you the characteristic length in which the wave can propagate. And beyond this length, the wave amplitude is going to be negligible. And so in this 7.1, I talk about electromagnetic wave in a piece of conductor. And we start from the definition of the current inside an ohmic material. And then we put the current expression into the Ampere's law and derive the skin depth of the wave penetrating into a piece of conductor. And you can see that for higher frequency wave and also for higher conductivity material, the skin depth is going to be smaller. So this means that an electromagnetic wave is going to be more difficult to penetrate into a piece of conductor. And so this is about a wave propagating into a piece of conductor. And basically, there's a strong attenuation for a wave inside a piece of conductor because of the frequency and also conductivity.